part 2 of lesson 2 in chapter 2, more on polynomial functions. Remember, a polynomial function might only have one term. If it has one term, we call it a monomial. If it has two terms, we call it a binomial. Three terms, we call it a trinomial. And if it's a polynomial, you know that the exponents have to be non-negative integer exponents. So, a little bit of review. Example 4 says, state the number of possible real zeros and possible turning points. Well, you can see here that since it's a fifth degree polynomial, there's 4 possible turning points, and then the possible zeros should be 5, same as the degree. Now, if you look at the graph, there's actually only 2 turning points. It doesn't actually have 4 turning points, but the possible turning points is always 1 less than the degree. So then it says determine all the real zeros by factoring. So if we take the x to the 5th minus 6x to the 3rd minus 16x, set it equal to 0. Take an x out of everything. That allows us to factor this. We need to have an x squared at the beginning of each set, because x squared times x squared gives us x to the 4th. We would need a negative 8 and a positive 2, which means our solutions would be 0. Now, if we set x squared plus 2 equal to 0 and solve it, that's going to give us an imaginary solution, plus or minus the square root of 2i. And right now, we're only concerned about the real zeros. So I don't need to identify those imaginary zeros. But if we set x squared minus 8 equal to 0 and solve that, that's going to give us x equals plus or minus the square root of 8, which we should probably simplify that into 2 square root of 2. Well, 2 square root of 2 is roughly 2.8, 2.9. So we've got positive 2.9, negative 2.9, and 0. And if you look at the graph, sure enough, it is crossing at positive 2.9, negative 2.9, and 0. Example 5 again says, state the number of possible zeros and turning points for this 4th degree polynomial. So if it's a 4th degree polynomial, the possible turning points is 1 less than the degree, and the possible zeros is the same as the degree. And now if we solve for these by factoring, we set this equal to 0. I can take out a negative x squared, leaving me with x squared plus x minus 2. That allows me to break that down into x plus 2 and x minus 1. And so our solutions end up being x equals 0, x equals negative 2, and x equals 1. And these answers should correspond with the graphical solutions. We can see it crosses at 1, at negative 2. Now at 0, it actually touches. It doesn't cross. It touches at 0. And we're going to talk about repeated zeros here in just a second. So one more example of the same kind of problem. You can see here we got a 3rd degree polynomial, so the number of possible turning points is going to be 1 less than the degree. Number of possible zeros is equal to the degree. And now if we try to find the zeros by factoring, set the equation equal to 0, we could take out a negative 2x. It leaves us with x squared plus 2x minus 8. That can be broken down then into positive 4 and negative 2, which means my solutions are 0, negative 4, and 2. And these answers should make sense with the graphical solutions. We should see it cross at 2, cross at 0, and cross at negative 4. So now let's talk about when you're given a function in a factored form, like you can see this one. Okay? It makes it really easy to identify the zeros when it's in a factored form. So here's the equation. I can say that my zeros are at 0, negative 3 over 2, and 1. So the directions say apply the leading term test. Well, we're not going to write anything down for the leading term test. We're just going to be able to look at this equation. And since it would be an x to the 4th, you know, if we got rid of those parentheses, we would have a 2x to the 4th as our leading coefficient and exponent. So that's the leading term test, is just understanding what the graph would look like. Part B, determine the zeros and state the multiplicity of any repeated zeros. Well, I've stated the zeros, but if you look on the graph, since at positive 1 it doesn't cross, it just touches, we say that it has multiplicity 2. That counts as a repeated 0. And that should hopefully make sense because right here, you can see that we've got a factor that's raised to the second power, so it's a repeated 0. And then part C says find a few additional points. You don't have to do that. And then part D says draw a graph. So what I'd like you to be able to do, and certainly you can use your graphing calculator to help you, but you should be able to draw a sketch based upon having the zeros and knowing the end behavior. Well, we know that this is a touchdown guy, both ends going up. We know that it's crossing at 0, crossing at negative 1.5, and touching at positive 1. So off of that, I know that my graph should have to look something like this. And that's the kind of sketch that I'm looking for. Next one, you can see that it's easy to identify the zeros. We'd have a 0 at 0, a 0 at 4, and a 0 at 1/3, and that would have a multiplicity of 3 because we've got an exponent of a 3 on that factor. So there's our zeros stating the multiplicity. This is a disco guy, Larry. Left side goes up, right side goes up. Sorry, left side goes up, right side goes down. And then part D, drawing a sketch. Now when I draw this sketch, this is going to look a little bit different. We know that the x-intercepts are at 0, 4, and 1/3. Okay. And so the graph would have to go like this. Now at this 1/3, it crosses, but it doesn't cross right through at 1/3. It takes on a cubic shape. So it's going to be half of a parabola down and half of a parabola up anytime the multiplicity is 3. So it doesn't go straight through, it has a little curve to it. Now if you look at this graph, this is a picture of a graphing calculator. It doesn't look like you see that same kind of display, that same kind of curve as you see right here. So let me take you to the graphing calculator and show you. Here's the equation. If we graph it with just a standard window, we get a graph that looks like this. But if we were to zoom in, you're going to see that we actually do have that behavior. So I've kind of zoomed in. In fact, let me zoom in just a little bit more. Let's just go up to 2 on that. So you can see that right here, we do have that cubic behavior. It kind of flattens out a little bit, then it crosses the x-axis. So it's half of a parabola up and half of a parabola down. Last example, same kind of problem. It says for each function apply the leading term test. Well, this one would be a disco guy, Larry. Left side goes up, right side goes down because the degree is odd and the leading coefficient is negative. Determine the zeros. Well, to do that, we'd want to factor this. So I'm going to take a negative x out. Leaves me with x squared minus 2x minus 8. From there, I can break that down into an x minus 4x plus 2. So our zeros are 0, 4, and negative 2. None of these have multiplicity 2 because each of those factors is just raised to the first power. Find a few additional points, don't have to do that. And then draw a sketch. Well, when we draw this sketch, we know that it's a disco guy, Larry, so left side goes up, right side goes down. We're crossing at 0, 4, and negative 2. So my graph's going to have to look something like this. Those are the kind of sketches that I'm looking for.